So, hello everyone. Welcome to the One World seminar on the mathematics of machine learning this week. It is my great pleasure to welcome Qin Li from the University of Wisconsin in Madison, where she is an associate professor. And she's going to give this week's presentation on the mean field theory and inverse problems from Bayesian inference to the overparameterization of networks. And so thank you very much for joining us. The floor is yours.
Thank you. The pleasure is really on my side. It's really my great pleasure to be invited and present here. I would like to talk about, as you see, the mean field theory in inverse problem. And I'm going to have two examples that uses a mean field theory. One is a Bayesian inference, and the other one is an over-parameterization of neural network. So as you see, this is a very long title. So to me, inverse problem is a set of problems that we work on, and mean field theory to me is a toolbox. So it's an argument that people can use to connect two sets of mathematical description, and we are going to utilize this argument to explain the validity of algorithms. And the algorithm that I would like to discuss, on one hand, I would like to discuss the optimization of neural network. There's a zero loss property that we would like to explain why gradient descent, even though the energy function is not convex, can still descend you to the global minimum. And on the other hand, I would also like to use mean field theory as my mathematical tool to explain why some Bayesian inference, Bayesian sampling algorithm would work. So to me, inverse problem is challenging, and mean field theory as a toolbox is rusty, and Bayesian sampling is colorful, and over-parameterization is heavy. Therefore, the color code over here. So let's. I know there are lots of experts in the audience, but still, let me still bore you 5 minutes to explain every word that I put in the title, so we have the common ground. So what do I mean by inverse problems? So forward problem, let's think about the analogy in linear algebra. Forward problem is you give me the matrix and you give me the input and I compute the output. So that's a forward problem. There are two kinds of inverse problem. Number one is you give me the output and you still tell me your machine, and I'm reversing the process, trying to find what is this input that produces output. So this is one kind of inverse problem. The other kind of inverse problem, which is more interesting, is this matrix or this machine that you are cranking is not known. So what you can do is to prepare a lot of input-output data. So you give me a lot of xi, yi data pairs, and I'm utilizing these data pairs to reconstruct your machine, in this case, a matrix A. So let's extend it to the nonlinear version. In the nonlinear version, you have this machine, and this machine is parameterized by the parameter theta. And what you can do is to insert your incoming input into this machine, and the machine produces you the output. So what you want to do is you want to reconstruct this parameter in your machine so that you can match the input and output data pair. So sometimes this parameter is a finite dimensional vector. And when that happens, people sometimes call it parameter identification. And for us coming from the mathematical world, theta can be a function. When it's a function, it's an infinite dimensional object. And when this happens, we are trying to reconstruct the function, and we call it the inverse problem. Okay, so numerically, in inverse problem, typically people have two technicality. One is the optimization structure, and the other one is a Bayesian formulation. So optimization is relatively easy. So what I do is to reconstruct or look for this parameter theta so that the mismatch between the data that you measure and the data that you can produce by the machine, this mismatch is minimized. So this is to look for one particular configuration, the mismatch is minimized. So that's under the optimization framework. In the Bayesian framework, the situation is slightly different. The Bayesian takes a probability viewpoint. It says, I do not believe there is one single theta that produces the data. but rather there are many kind of configuration of theta that allows you to match with the data pairs. But each configuration have different probability, therefore you want to write down the probability measure. So that's a Bayesian formulation. So in some sense, optimization looks for this particular configuration that minimizes the energy, and Bayesian in some sense is slightly more challenging because it looks for the whole landscape of the probability measure. I would like to have one word about this. We usually say that the Bayesian is an extended version of the optimization in the following sense. So optimization, you're looking for one parameter that makes a mismatch, the minimum. So you look for one configuration. In Bayesian sampling, it's true that you're looking for the whole distribution function. But if your objective function is a function null of distribution function, you can view it as you try to find the distribution so that the function null is minimized. So that sort of translate the Bayesian sampling problem or Bayesian inference problem back into the optimization problem. So for example, one such function null is the KL divergence. You're looking for Z distribution P so that the distance between P and your target distribution Q is minimized. So in some sense, suppose you're doing the gradient flow or gradient descent for the minimization, you're looking for the X so that Fx is minimized. One thing you can do is to follow the gradient flow. So you construct the ODE, and this ODE basically tells you from one iteration to the next iteration, you basically descend along the gradient with a small time step h. If you translate this gradient descent to the Bayesian formulation, you can do the same thing. I'm looking for P so that this function null is minimized. Therefore, we can write down the PDE, the gradient flow for this probability measure. So you're looking at the PDE that tells you one particular point in the function space that minimizes this function null. So in some sense, Bayesian sampling or Bayesian inference can be viewed as an extended version of optimization. So that's about inverse problem. So let's say a little bit more of what is a mean field theory. Mean field theory, I would view it as originated from statistical mechanics. So this is a following physical system. So you are given a physical system, and this physical system is composed with a large number of particles, and all these particles move around. The motion of these particles is governed by the forcing term composed by all its neighbors. So I look at the dynamics of one particle x1. It is a force pushed around by all its neighbors according to the forcing function f1. And I have another particle, x2, it gets pushed around by the function f2 with the argument being all its neighbors. So each particle follows one ODE, and there are n particles, therefore I have n coupled ordinary differential equation. So that's one way to describe this physics. So you write down the list of trajectory of each particle. Therefore you get n coupled ODE. Another way to describe the dynamics of this system is to forget about the trajectory of each particle. Instead, you say that I'm more concerned about the full distribution of these particles. So instead of tracing the trajectory of the particles, I trace the evolution of the distribution. If you have a finite number of particles, you take the summation of all this delta measure, and that's your probability of all these particles. So instead of saying that x1 moves around with certain rule, x2 moves around with a certain rule, you say your probability measure get moved around propagating time according to a forcing function. So of course, the specific form of this capital F depend on this little f that we talked about. So the way that neighbors affect you or influence you will get reflected in this F operator. Okay, so here is the thing. You have one physical system, but two distinct description of the physical system. One is a coupled ODE system, and the other one is a partial differential equation that characterize the dynamics of the distribution function. So these two ways of characterizing the same physical system should be somehow unified. And that goes back to Hilbert in 1900 when he proposed a Hilbert number 6 problem. That is, you have the same physical phenomena, you should unify two different descriptions. So that's what mean field theory is about. Mean field theory gives you this argument that tells you how do you translate the coupled ODE system to the PDE. Okay, so that's a mean field theory. So on the first look, you would think that inverse problem is some sort of, you come from the real practical world, you formulate an inverse problem. And mean field theory is a totally different thing. It's an argument that you can use to characterize or to unify two distinct descriptions of a physical phenomenon. So why mean field theory is useful in inverse problems? I'd like to give two examples. From the optimization side, I'd like to argue that mean field theory is a set of arguments that can explain the zero loss property of the neural network that is over-parameterized. So a neural network that is gigantic, have many, many layers, and on each layer you have many, many neurons. So you can view each neuron as one particle. And if the neural network is over-parameterized, that means there are so many neurons in this neural network. And therefore, moving around its configuration of the neural network can be viewed as changing the position or configuration of these particles. So you can translate the dynamics of these particles into the dynamics of the underlying distribution function. Similarly, in the Bayesian side, there are some algorithm out over there that says in order to find sampled according to this distribution function, instead of doing it one by one, I'm going to just put down a large number of particles all together and evolve them. Hopefully, after some certain time, these particles can be viewed as they are sampled from this distribution. So over there, you have a large number of particles as well. And mean field theory can be the argument that translate the dynamics of all these particles to the dynamics of the distribution. So in a sense, so these two problems can be unified as I'd like to translate the particle presentation to the statistical presentation. Instead of tracing the trajectory of each particle, in here is a neuron, in here is a samplers, I would like just to describe the dynamics of the whole distribution function. Okay, so that's a general framework. Let's get down deep into the details, the over-parameterization of neural network. So neural network is such a fascinating thing that everybody is excited about recently. So there are many aspects of neural network that people conduct research about. So the particular topics that I'm concerned about is the so-called zero loss function, in the sense that you have the following neural network. This, let's say the number of layers is L, and L is big. You have many, many layers. And on each layer, you have M, there's many neurons. And M is really, really big. So you have a very wide neural network as well. So what you do is to put in the input X, and this X goes through the composition of many, many functions. And in the end, you construct the output according to this neural network, and you hope the output would be similar to the data that you gave me. So there are many aspects many questions that you can ask. For example, I gave you an arbitrary function that maps the incoming X to the outgoing Y. how can this function be approximated by the neural network? So that category of research falls into the category of approximation theory. And I know there are a lot of experts in the audience that does the approximation theory on that side. So this is not something that I'm talking about today. What I would like to talk about is the so-called zero loss property. That is, so you formulate your neural network according to the configuration of the neurons. So you would like to configure these neurons into some certain formulation so that the output of the neural network truly matches the data that you gave me. So I'm looking for the configuration of this theta L M so that the neural network truly gives you the match of the perfect match of the data that you gave me. So over there, you can construct a loss function and you're looking for the minimum of the loss function. Unfortunately, this minimum, the loss function is not convex. And for non-convex optimization, it's very hard to find its minimum. However, experience told us that just by running the gradient descent, the first order optimization method, you nevertheless find the minimum. So that is very intriguing and very interesting. So why the first order method can overcome the non-convexity of the problem and find the global minimum of the problem. So that's a so-called the zero loss property of the deep over-parameterized neural network. And this is a problem that I'm interested in. So let's be a little bit more precise here. So all these neurons are configured according to the parameter theta. There are two arguments for the theta. The first argument tells you which layer you are in, and the second argument tells you which neuron you're looking at on this layer. So I'm looking at the setting when the number of layers and the number of neurons per layer, they are both very, very big. So I'm in the over-parameterized regime. Okay, so suppose I'm looking at the residual network. The residual network can be written in the following way. From the previous iteration, from this layer to the next layer, what you do is just to sum up the contribution of all the neurons on this particular layer. So from L to L plus 1, I sum up this activation function. This activation function is parameterized by theta L using the mth neuron, and I sum them all up. So my final goal is to translate this updating formula of the neural network into the ordinary integral equation. So previously, what you need to do is to find the configuration of the theta so you have the best mismatch. And now theta disappeared when you do the translation into an ordinary integral equation. The theta parameter is replaced by rho parameter, with this rho being your probability measure of all the theta. So in some sense, previously you're looking for the configuration of the theta. Now the training process becomes I'm looking for the configuration of the probability measure. Now the question is it true that I can translate the training of theta to the training of rho, and why the training of rho can get you to the global minimum? So the general strategy of this whole theory is the following. We write down the evolution of the residual network, and by conducting the so-called continuous limit, that is to send L goes to infinity, the number of layer goes to infinity, I translate the neural network into the ordinary differential equation. Furthermore, by sending the mean field limit, that is to send M goes to infinity, by conducting the mean field limit, I'm translating the a coupled ordinary differential equation into an ordinary integral equation. So this is conducted on the neural network level. Similarly, your parameter is changed as well. In the original ResNet, you have L layers, and on each layer you have M neurons. So you have a large number of neurons to train as your parameter. And in the ODE and OIE level, these parameters are replaced by a class of functions, and then finally, one probability measure. So the training process, previously you have the ordinary differential equation to train these parameters. It's a class of numbers or a class of vectors. And in the end, this training process gets translated into a gradient flow for this limiting probability measure. And finally, you say that this training process and this training process, they are equivalent in some sense. So analyzing the training process of the original neural network is the same thing as analyzing this gradient flow partial differential equation. And over there, you show that this gradient flow converges you to the global minimum. Therefore, you flip it back to say the training process of the original neural network gets you to the global minimum. So the proof strategy is to conduct the 3 steps. So let's be a little bit more detailed. So the first step is to conduct the continuous limit. This is to send L goes to infinity. So what you do is, this is my original neural network formulation from one layer to the next. You sum up the contribution of each neuron on this layer. So I denote this little h as 1 over L. As L goes to infinity, h goes to 0. So now you move this ZL to the left-hand side and divide by h. This is exactly the forward Euler method for an ODE. And this ODE tells you that the dynamics of this Z in the continuous time follows the right-hand side as a summation of all the forces. These forces combines the contribution of each neuron. So that's on the neural network level. So the structure of the neural network gets translated to the ODE, and the parameters are translated as well. On the neural network level, you have L layers, and on each layer you have M neurons. Now you regard this theta Lm as M's neurons evaluation of L times little h, with h being your step size. Then this theta becomes the discrete version of the function. There are M, those many functions, and you evaluate the function at a discrete time. The loss function gets translated as well. Previously, you're looking for the mismatch between the labels that you give me and the labels that you compute through the neural network. Now my cost function is similar. I'm looking at the mismatch between the labels that you give me and the labels that you compute according to the ordinary differential equation. So the training process, for the gradient, if you conduct a gradient descent, the training process is to say this theta, or this collection of parameters, they descend in the gradient direction of the cost function, and in the limit, the theta becomes a class of functions. So you're updating a class of M, those many functions, according to the Frechet derivative of the cost function on these functions. So you no longer have the gradient over here, you have the Frechet derivative on the right-hand side. So that is to conduct a continuous limit. When you send L goes to infinity, therefore the step size becomes 0. Okay, so that's a continuous limit. And then we conduct the mean field limit. The mean field limit has the same story. Previously, after conducting the continuous limit, we have the ODE that characterize the continuous version of the DNet of the ResNet. And over here you have a summation of all the forces. This forces is parameterized by your continuous parameters theta m. So naturally you have the expectation format, right? So you have theta m, those many parameters, and you sum them up to force the total forcing term. So you assume that all these parameters, all these neurons, they are drawn from one distribution. So theta as a trajectory is drawn from a probability measure rho. So this summation is then changed into an integral. Therefore, you replace this summation by the integral. With respect to the probability measure, that you believe is the underlying probability measure of the theta. So the neural network changes from an ordinary differential equation to the ordinary integral equation in the mean field limit. So on the neural network structure, we translate the ODE to OIE. And similarly, the parameter and the loss function are changed as well. Previously, you have M trajectories of function. Now you believe this theta is drawn according to the probability measure. Now your parameter is this probability measure. So the training process, previously you look for the configuration of all these functions. So you descend according to the Frechet derivative with respect to these functions. Now the training process is to train for rho, and rho satisfy a PDE. Your gradient flow you into the direction where the cost function is minimized as well. The gradient flow is written down in this form. Okay, so finally we summarize. My true dynamics of the deep neural network gets translated to the ordinary integral equation. The training process, therefore, is translated from the gradient descent to the gradient flow of the underlying probability measure. Then our question is, when you conduct this translation, you're saying L and M goes to infinity. How do I rigorously justify how big this L and M need to be so that the cost function from the original parameter and the cost function from the new probability measure, they are truly close to each other? This is the essence of our work. Our theorem suggests the following. Our theorem suggests that you need to have 1 over epsilon, those many layers. And on each layer, you need to have 1 over epsilon squared times eta, those many neurons. And under this condition, you can say that the cost function from the original neural network and the cost function from the limiting procedure are epsilon away from each other. And you can say this with a confidence of 1 minus eta. So the proof is a little technical. I do think this proof is very technical, but I would like to argue that the result is not surprising at all, especially the rate of the size of L and M is not surprising. So if we look at the size of L and the size of M, for example, let's take a look at L. L is a number of layers. So from the previous procedure, we find that, from the previous procedure, we find that L serves as the time dependence, right? The L is the number of time intervals that you chop your neural network from time equals to 0 to time equals to 1. You chop it into L pieces. And on these L pieces, you conduct the forward Euler. And forward Euler is a typical first order algorithm, first order method. So for the first order method, the convergence should be first order as well. So if you have epsilon accuracy, so if you need epsilon accuracy, the number of layers or the size of this L should be 1 over epsilon. So that makes a lot of sense. The dependence on M also makes a lot of sense. So M is the number of neurons per each layer, right? So on this M, we conduct the mean field limit. We consider this M as M particles, and we are trying to show the convergence in terms of the number of the particles. This is basically Monte Carlo, and for Monte Carlo, the convergence is 1 over square root of M. Therefore, you require this to be smaller than epsilon, then M should be 1 over epsilon squared. So this rate is also makes a lot of sense. So the eta dependence, previously I was asked about the eta dependence. I do not claim the sharpness of the eta dependence. The proofs on eta over here is we didn't make it very sharp. So this eta comes from the Markov inequality. So that's a very weak, very loose bound. So maybe there's a chance to increase the rate of eta. Okay, so finally, let's come back to our summary. We have completed both the continuous limit and the mean field limit, and we translate the neural network into the ordinary integral equation and the procedure of the training procedure from the gradient descent to the gradient flow. And for the gradient flow, we need to show that the gradient flow converges to the global minimum. The cost function is truly 0 in the limit. So this part is a weak part of our result. Our result, we haven't tried really hard to show the global convergence to the global minimum. So the assumption that we put over here is relatively strong. So the assumption on the activation function is okay. So it's a continuous function with a derivative, etc., having algebraical growth in theta and x. So that part is fine. And also mu is the size of your input data that is compactly supported. This also makes sense. However, these two assumptions are relatively strong. We assume that the PDE converge. In pseudo training time as the training goes to infinity, we assume that the PDE converge to a function on theta and t. So we cannot show the convergence, we assume the convergence. And furthermore, we assume that the convergent, the limit function has a full support in theta. So that's another strong assumption. But anyway, based on this assumption, we can show that the limiting of the cost function as you train your neural network, as you run this gradient flow equation, the cost function is going to 0 as your training time goes to infinity. So the proof is because of the strong assumptions, these two strong assumptions, the proof is not difficult at all. So we believe there is a lot of room to improve these assumptions. So I should say that the first assumption is really just we don't know how to show the convergence, so we have to assume it. And the second assumption is relatively technical. So in the proof, in order to get to the global minimum, this rho having the full support allows us to quickly get to the gradient of E being 0, this condition. So this is a technical assumption. Without these two assumptions, especially without the first assumption, I haven't seen any result. So there's a lot to do. Okay. So finally, we summarize. We put all the 3 steps result. We lump them into one theorem that says your training time is really big. The size of the neural network is really big. Under this condition, you can show that the cost function or the mismatch that you are trying to minimize is truly convergent to a value that is smaller than epsilon with high confidence. Okay, so this is, we have some expert in the audience over here, and the 2 papers we have put onto archive. The first paper is under revision. Okay, so that's our first explanation of using the mean field theory as an argument to explain the 0 loss property of the deep neural network. So as you can see, this mean field theory is kind of very powerful in translating the dynamics of the neurons to the dynamics of the limiting probability measure. Okay, so my next example is to use mean field theory to explain the validity of the Bayesian sampling algorithm. So Bayesian sampling algorithm comes from Bayesian inference. Bayesian inference, as many of us know, so the forward problem is you have a parameter in your machine and you crank your machine, you get the data. Then the inverse problem is to reverse the procedure you measure the data y, and you invert this forward map to reconstruct your parameter u. And over here, you have some measuring error that is assumed to be there as well. So the Bayes rule tells us that if u is the parameter of the machine, there is no single u that gives you the match of the data, but there is a class of u. There are a lot of configuration of u that can give you this data. So it's just different u have different probability. So the Bayes rule said the distribution of this u, in order to find out how this u get distributed, the posterior distribution is a multiplication of the prior distribution with the likelihood function. Prior distribution tells you how u is sampled from before you conduct any experiment to obtain this y. And likelihood function tells you, suppose your u is a particular value, then how likely you measure the data y. So you check the match between this y. But nevertheless, the posterior distribution can be viewed as a product of two functions. So finally, what we want to do is to find samples in this posterior distribution, especially when your u is high dimensional or k, for example, with k really, really big, you want to know how to find this u, how to find the distribution of this u. U is in a high dimensional space. So simply drawing the distribution of U, that's just not possible. You want to find the samples according to this probability measure. So finding the samples from one given probability measure, that's a very interesting problem that had triggered a lot of study. And historically, I think Markov chain Monte Carlo is probably one of the most famous algorithms. It's a class of algorithm, and there are many variations. So on this method, however, it says I start from one sample, and I know this sample is not sampled from the posterior distribution, but I'm going to run it according to some certain iteration formulation, and the iteration after a long time, it's going to get me to the point it can be regarded as sampled from the posterior distribution. So all of them are the same. If you need a different sample, then you need to restart this process again. So suppose you need n samples, you need to run n particles independently. So that's a very classical view of finding samples according to the Bayesian inference. The class of method that we would like to discuss today is the ensemble type method. So the so-called ensemble, as you can imagine, this word ensemble means you don't have one particle and you run it many, many times, you get this sample sampled according to the posterior distribution. But rather, at the initial time, you tell the national lab, for example, you run their CPU, you tell them that initially I need to run 1 million samples, for example. You put 1 million samples all together and you run you update this 1 million samples all together. So these samples will talk to each other, and this talking will communicate the information from all these samples. And hopefully after some finite time, all this 1 million samples, it looks like they are all sampled according to the posterior distribution that you're looking for. So this is the so-called ensemble method. In a way that you have a prior distribution, and on top of it, you multiply the likelihood function and you get the posterior distribution. So in a way, what we do is we sample initially a bunch of samples according to the prior distribution. And then what I do is I introduce a motion to each particle. For example, this particle moves this way, this particle moves this way, etc. I introduce motion to each particle, so the particles get moved around. And after some time, it looks like these particles are sampled according to the posterior distribution. So there are many questions to be asked. The very first question is, what kind of motion could lead the distribution of the particles to the correct target distribution? There are many arguments. Sometimes people say that interacting particle system, they feed information to each other. So there's a chance that because I get information from you and we evolve together, so there is a chance that we save some computational cost. But whether it's true, at least to today, we haven't seen a clear difference that the ensemble method is truly more useful than the classical MCMC. So this is a debatable question. So both of them have many interesting algorithms, but which one wins, we still don't know. At least I think you still don't know. Okay, so under this Bayesian inference, there are two algorithms that I'd like to discuss. These two algorithms are very, very similar. One algorithm is the ensemble common inversion. Ensemble common inversion, when it was introduced, it was not really for the Bayesian inference, it was for optimization. But later on, people find out that it works for Bayesian as well. Okay, so ensemble common inversion introduced time in a very straightforward way. So it says my posterior distribution is proportional to my prior distribution multiplied with the likelihood function. And the way I introduce time is just simply to add this time in the exponential function. So very soon, very quickly, that you see that when t equals to 0, this term disappears. You come back to the prior distribution. And when t equals to 1, that is exactly your posterior distribution. So your so this function is a linear interpolation on the log scale between your prior and the posterior. Okay, so that's on the function level. Now the question is, how do my particles sense this motion, right? So the algorithm is written down in this way. The original paper came out about almost 10 years ago. It says, initially you tell me how many samples you need, and I divide my time into m pieces. So my step size is h, and y is the data that you gave me. Initially, you sample all these particles according to the prior distribution, and the prior distribution, all these samples get run around for a long time. And after a certain time, I collect all these samples, and I hope these samples collected behavior is a posterior distribution that you're looking for. These three tedious steps, they are tedious, but they came down to the Euler-Maruyama method for the stochastic differential equation. So now the question is, Can I
interrupt you briefly? There is a question in the chat, which I think it was 2 slides ago, which says, okay, isn't it the ergodic hypothesis that average over time is the same as average over ensemble?
Yes. That's a very good question. I think that's what people do usually. People say that I run one sample, and after some certain time, I call this sample is my sample according to the posterior distribution. And you continue running it, right? If you continue running it after some certain time, you call it the second sample. And because this second sample can be, you can sort of view the second sample is independent from the first sample, and you have a class of samples. That's true. So what I want to say is this ensemble common sample, it's just not one single particles running in time, but rather you have a whole lump of particles running, and they talk to each other and feed each other information. So that's sort of the philosophical difference between these two different type of sampling algorithms.
Thank you. If there's any more questions, yeah, thank you, says the chat.
Oh, thank you. Oh, thank you. Right, so the distribution function, on the function level, we know that the function is a linear interpolation on the log scale between prior and posterior distribution. And on the algorithmic level, each particle evolves according to the stochastic differential equation. So now the question is, what is the relation between this stochastic differential equation for each particles and the functions that you're trying to recover, right? So what we do over here is to write down a partial differential equation, and this partial differential equation can be regarded as the mean field limit of the stochastic differential equation. You have a lump of particles, and the distribution of these particles follows a partial differential equation, and this partial differential equation is exactly the equation that carries you from prior to the posterior distribution. So the proof of the whole recipe can be divided into 3 sections. Let's go backwards. From the algorithm, you let the algorithm step size goes to 0, the Euler-Maruyama method tells you that the algorithm is simply the Euler-Maruyama discretization of the stochastic differential equation, and you assume the number of particles goes to infinity, the mean field limit of this particle system gets you to the partial differential equation. And the partial differential equation is the equation that carries you from the prior to the posterior distribution. Okay, so there have been a lot of work in this direction. I would like to mention that our work, the contribution of our work, only lies in the mean field part, in the sense that we connected the stochastic differential equation with the partial differential equation. So this part, Andrew Stewart and Schilling, they did some studies over here, and this part is relatively straightforward. I think it's just a calculation, basically. Okay, so the theorem that we prove is the following. So we basically say that ensemble common inversion as an algorithm, it converges as the number of particles goes to infinity, and the convergence rate is 1 over square root of m. So that's probably the best convergence rate you can hope for, right? The Monte Carlo is just 1 over square root of m. So we basically get the optimal convergence rate. Okay. So that's one algorithm, ensemble common inversion. The second algorithm is very, very similar. It's in terms of analysis, it's very, very similar. It's ensemble common sampler. One of the organizer, Franka Hoffman, she was involved in the designing of ensemble common sampler about 2 to 3 years ago. So the idea is we start from the classical Landry Monte Carlo. The classical Landry Monte Carlo says each particle, they descend according to the gradient, and on top of this gradient information, you add some Brownian motion term. So each particle, they just evolve by itself. You look at this formulation, xi doesn't talk with xj, for example. And then they come up with this algorithm called Ensemble Landry Monte Carlo, in the sense that each particle not only descend according to its own gradient, but also I multiply this gradient with a term that is a covariance of all these particles. So the covariance is a summation of all these particles influence each other. So the reason they do this is to look for possibly to look for a gradient-free method. If you look at it, the covariance of x multiply with the gradient of f, very, very quickly, this gradient of f combined with the difference of xi minus x bar being the mean of x, it sort of simulates, it's not exactly the same, but it simulates the difference of fi and the mean of f. So if you can really translate the covariance, the product of the covariance with the gradient into the covariance of x and f, you basically achieve an algorithm that does not require the computation of the gradient. So it's a gradient-free method. And in inverse problems, a gradient-free is a very important feature. It's an ideal property. Okay, so now the question is, this is an algorithm that they design. Each particle, they move according to some gradient information and the Brownian motion. Now the particles interact with each other according to this covariance term. So now the question is, if you have so many particles move around, what is the collective behavior of all these particles? And that is the mean field part. The mean field part is to justify if you believe there's an underlying probability measure of all these particles, then the underlying probability measure rho satisfies the following Fokker-Planck equation. And this Fokker-Planck equation translates you from initial whatever distribution that you gave me, translate in infinite time to the target distribution that you want, which is E2 minus F. So the mean so the original paper was this one, and what we did is to prove the mean field part. So similar to the previous algorithm, we translate the algorithm into the stochastic differential equation, and the stochastic differential equation is characterized the trajectory of a lot of number of particles, and you seek for the collective behavior of the underlying probability measure by conducting the mean field limit. You get a Fokker-Planck equation, and the Fokker-Planck equation's equilibrium in long time is the target distribution function that you want. Okay, so finally, the result that we have, we show that the difference between the PDE and the coupled SDE is 1 over square root of n. So as the number of particles goes to infinity, you converge to the PDE. This is a collection of the reference. This is the original paper for EKI. This is the original paper for EKS. And as you can see, I'm not very good at giving titles to my paper. So in these two papers, we analyze the mean field structure of EKI and EKS respectively. Okay, so let's finally summarize a little bit. In inverse problem, we are given the data. We are given the data pair, the input and the output, and we try to figure out the parameters in your machine. Mean field theory tells you how do you translate the trajectory of a large number of particles into the dynamics of the underlying probability measure. So mean field theory is this toolbox that you can use to answer the validity of Bayesian sampling algorithm and the zero loss property for over-parameterized neural network. I would like to invite the audience to brainstorm. For example, there are a lot of algorithms out over there that you use a large number of particles altogether. You train a larger number of particles altogether. So when you have an algorithm like that, the mean field theory could be a very useful tool to transform this formulation into a PDE that is easier to handle. With that, I would like to stop. Thank you very much for your attention.